Number 1 asks us to sketch or describe the figure in step 4 and step 15 of this pattern. So when you're looking at this pattern, there's probably lots of different ways you can try and make sense of it. So for me, I guess when I was looking at it, one of the things I saw was obviously this kind of blank spot here. So I looked at it as this, and then I saw that we added another one, but I wasn't sure how to really write that in a pattern, especially in something like this. But I did, through notice that this was like 2 by 2 and this was 3 by 3. But then I wasn't sure over here. So then I was like, okay, well, it's probably going to be 4 by 4 and we're going to have a square here. And that's where then I realized that this was a missing square. And maybe we could look at it as this square has been moved up to here. So we start with this 2 by 2 square in step 2, and we move this one to that top right corner. And so if we think about that here in this one, right, we have a 3 by 3 square, and we move this square to the top right corner. So for step 4, then I was thinking, so if you wanted to write it in words, right, we're going to have a 4 by 4 square, and the lower left square will be moved to the top right corner. If you want to be writing it in words, and then that would be for step 4, right? And then for step 15, it would be the same thing, but it would be a 15 by 15 square with that lower corner one moved up to the top, right? So if you can almost think of this one not being here and it was just down here, right? You see that 2 by 2 square. So then this would be a 2 by 2, which would give us 4 total squares once we, move it up. And then same thing here. If we think of this one not being here and we move it down here, now we just have a 3 by 3 square for our total. And this one is just a 1 by 1. So then that 4 by 4 in step 4 is going to have 16, right? Because we'll really just have a 4 by 4 square and have 16 squares. And then in the 15th stage, we'll have a 15 by 15 square, and that'll give us 225 of those small squares. Then it wants us to write an equation of the relationship between the step number, n, and the number of squares, y. And so if we think of replacing this step number with an n, then this should be an n by n square. So the number of boxes that we have would be n times n, or another way to say n times n would be n squared. So whichever of those you want. And then how does that relate to your pattern? And really, because we make a square with the dimensions of the step number. Right? So then our square is 1 by 1, 2 by 2, 3 by 3. If we move that kind of removed box or the box from that top corner back down into that missing space. Number 2, which expression represents the relationship between the step number and the total number of small squares in the pattern? So if we look at all of these, we see that they all have an n squared. So we want to be trying to figure out where we see that step number squared. And, this step 1 doesn't have any squares. But step 2, if I look at it like this, right, as a 2 by 2 square, and then we have this 1 square missing. So we really do have a 2 by 2 square, large square, and then we're erasing or subtracting 1 square from that, right? So we have 2 squared minus 1. And this one is a 3 by 3 square, but this one is missing. So we have 3 times 3 little squares, and then we're going to subtract 1. So that's like 3 squared minus 1. And so we see that step number coming into the pattern here. So if we had step n, then we could have n times n squares minus 1, or n squared minus 1, which is option B. Number 3, each figure is composed of large squares and small squares. The side length of the large square is x. So this big square here is x, this one is x, and this one is x. Write an expression for the area of the shaded part of each figure. So if we start in figure B, because it maybe is a little bit easier because there's no kind of missing space here. But remember, this is a square, so it's an x by x box. So this one wants us to write an expression for the area. So we find the area by multiplying length and width, which means we'd have x times x here, or x squared for each of these big boxes. Then these little ones are 2 by 2. So if we take 2 by 2, or 2 times 2, that equals 4. So each of these areas equals 4. And then we just need to total it all up. So we have x squared plus x squared for those big boxes. And then we have plus 4 and plus 4. So that would be an expression, or we could simplify it by saying we have 2x squared boxes, and then we have 8. So this would be the area of that whole shaded region. Now for figure A, you can think of it as like we are shading in, if we shaded in this whole thing, okay? So if I found the area of this whole entire section here, that's an x by x box, right? So that whole area there is x squared, x times x. Then we have these little pieces right here that are removed, okay? And removing in math is subtracting. And so we're subtracting each of these little boxes away. And if you remember, they were each a 1 by 1 box. And so the area of each of these is 1 times 1, which is just 1. So the area of every one of these boxes is 1. So we have to subtract out all of these 4 boxes to get our area of just the shaded region. So we have x squared minus 4 ones, and that's our total area. So that whole big x squared box minus 4 little unit boxes. Okay, number 4, here are a few pairs of positive numbers whose difference is 5. So difference means they subtract to 5. Find the product, so multiplication, of each pair of numbers, then plot some of the points to show the relationship between the first number and the product. So we'll do 1 times 6, which is 6, 2 times 7, which is 14, 3 times 8, which is 24, 5 times 10, which is 50, and 7 times 12, which is 84. Then we could plot these. So 1 goes with 6, and remember they want the first number with the product. So 1 and 6, 2 and 14, 3 and 24, 5 and 50, 7 and 84. So then it says, is the relationship between the first number and the product exponential? And remember that this means you'll have a common factor, or you'll multiply by the same number to get each of these, the next one. So you want to make sure that you compare the same jump in x. So this goes up 1 and this goes up 1. So I'm going to compare these products right here. So what do I have to multiply by? So 14 divided by 6 will tell me what I needed to multiply by. And in that case, it's 2.33 repeating. So we'll go 2.33 repeating to go from 6 to 14. And then 24 divided by 14 will tell me the factor that I needed here. And so that's 1.714. So then the answer to is this exponential is no, because we don't multiply by the same number, or no, because there's no common factor or common multiple. Number 5. Number 5 is actually exactly the same problem as lesson 1, practice problem number 2. So if you did that lesson, you can go back to it and look at your work for that one, or I'll explain it again as well. But it's exactly the same as lesson 1, number 2. So we have a rectangle whose perimeter is 20. And perimeter means we're going to add up all these sides. So we're going to have 2 of the same widths and 2 of the same lengths. So if we just add 1 length and 1 width, it's going to be 10, half of the perimeter. And this wants us to find the area, which means multiply them. So 1 times 9 is 9. 3 times 7 is 21. If our length is 5, then our width would be 5. And 5 times 5 is 25. If our length is 7, then our width would be 3, and the product or area would be 21. If our length is 9, then our width is 1, and our area would be 9. Then it says, without calculating, predict whether the area of the rectangle will be greater or less than 25 square meters if the length is 5.25. So if you remember back in lesson 1, we kind of looked at maximizing the product. And that happens here when the numbers are exactly the same. We get that maximum product. So if the numbers add to 10, the highest that they're going to multiply to is when they're the same, 5 times 5 or 25. So this is automatically going to need to be less, since this is not a 5. Because if we had a length of 5.75, we would have a width of 4.75, and that's going to multiply to less than 25. Then it wants us to plot these values, and they want us to plot the length and the area. Okay, so the length is this first column and the area is this one. So we will plot the 0.19, 321, 525, 721, and 9. Then it asks us, is this changing in a linear way? So do you see a line pattern here? And that answer is no, definitely not, because it goes up and then goes back down. And then is it exponential? And exponential either starts increasing slow and then gets faster and then increases forever, or it's starting high and then it decreases and then levels out. So it starts decreasing at a pretty quick rate and then levels out. Either way, this is not it, okay? Because this goes up and then goes back down. So this isn't linear or exponential. Number 6, here's a pattern of dots. Complete the table. So try and figure out the pattern. I think it's harder in the earlier steps, okay? But as you go on here, you start to notice in step 2 and step 3 that you're seeing a square, okay? So we see this square presenting itself here, and we see this square presenting itself here. So if we looked at it like that, we would have a square here, okay? And then in step 0, you'd also have this square, which is non-existent, right? So for step 3, this is a 3 by 3 square plus another dot. Here you have a 2 by 2 square with another dot. Here you have a 1 by 1 square with another dot. And then in step 0, it would be a 0 by 0 square, meaning it's not there, plus another dot. So when we look at filling this in step 1 or in step 0, there's 1 dot. In step 1, there's 2 dots, which you can just count. Step 2, there's 5 dots. And step 3, there's 10. So in step 10, this pattern would hold true, that we would have this 10 by 10 square, and we would have one more dot. So we'd have 10 by 10 dots plus another one. So 10 by 10 would give us 100, plus that extra dot would give us 101 dots. So then step n, we would have an n by n square, because the square dimensions matches the step. So we'd have n by n, and we'd have an extra dot. And so if we wanted to change that, we could say n squared plus 1. Number 7, Mai has a jar of quarters and dimes. She takes at least 10 coins, okay, so 10 or more coins out of the jar, and she has less than $2. So write a system of inequalities that represents the quarters, Q, and the number of dimes that she could have. So the number of coins that she has, the number of quarters plus the number of dimes, has to be at least, so that means greater than or equal to 10. So she has to have 10 or more coins. Then the value of those, so the value of each quarter is 25 cents. So we'll take 25 cents times the number of quarters. Dimes are worth 10 cents. So we'll take 10 cents times the number of dimes. And this number has to be less than $2. Okay, it cannot be equal to, it just has to be less than $2. So then part B asks us if she is able to have these possible combinations. So are the following combinations of coins possible? Okay, explain or show how you know. So first of all, they have to meet this first criteria, that there has to be less or greater than or equal to 10 coins, okay? So in part 1, we have 3 quarters plus 12 dimes, which gives us 15 coins. And 15 coins is greater than or equal to 10, so this is good. It satisfies that part of the system. Then we have to look at the value of each of these coins. So remember that we're going to take the quarters times 25 cents. So this is giving us 75 cents in quarters. And then we have 12 dimes. So we'll take that times 10 cents. And that gives us $1.20 in dimes. For a total of 75 cents plus $1.20 gives us $1.95 in coins. And that needs to be less than $2, which it is. So $1.95 is less than $2, which is good. So that means it satisfies both of these options. So this one is possible. Option 2 has 4 quarters and 10 dimes, which equals 14 total coins. 14 is greater than or equal to 10 coins. So we satisfy the first stipulation. Then we need to look at the value. So 4 quarters is worth $1. So we have $1. And then 10 dimes, so if we multiply 10 times 10 cents, that's also $1, which gives us a total of $2 in coins. Now, $2 is not less than $2. So this is bad, okay? It had to be less than $2, and this is equal to $2. So this combination is not possible because the value isn't under $2 or isn't less than $2. So then in part 3, we have 2 quarters and we have 5 dimes, which is 7 coins. And 7 is not greater than or equal to 10. So we do not have enough coins in this case, in which case we don't need to check the value. Okay, so this is no, there are not more than or at least, okay? So there are not at least 10 coins. Number 8, a stadium can seat 63,026 people. For each game, the amount of money that the organization brings in through ticket sales is a function of the number of people N in attendance. So that means that N is our domain, and the money is our range. So if each ticket costs $30, find the domain and range. So the domain is just how many people can be in this stadium. And so what we have here is you could have 0 people, okay, up to 63,026. So from 0 to 63,026. And if you want to write this with an inequality in here, you could say 0 has to be less than or equal to the number of people, which has to be less than or equal to 63,026. Then the range is the money that is being brought in by ticket sales, right? So you could have $0 in ticket sales, right? So we could have 0 for this, and you don't have to put a dollar sign with this, but you could have 0 up to taking this times 30, times 30. If you sold every single ticket. So if it was a sold out event, then you'd be at $1,890,780 that you brought in. So from 0 to 1,890,780. Again, if you want to write it with an inequality notation, did they tell us a variable for the money? They didn't. So we could just call it y. So 0 has to be less than or equal to y, meaning y has to be greater than or equal to 0. And then y has to be less than or equal to that $1.89 million.